Hello everyone, and this will be our last lecture in spectrum analysis, and in particular we will be focusing on how do we calculate power spectral density. So in certain aspects of engineering you may be required to calculate the signal power as an estimate or for a particular frequency band, and the time domain equation for this is an integral form if you're trying to get for the entire signal, where the integral here represents the entire periodic time you're trying to get the signal power for regarding the signal. And this is actually for the signal power estimate in this case. Now, because that's a time integral, it's not really easy to do automatically, but because we can discretize this into the DFT or the FFT, we actually can utilize this in the discrete time domain. And in order to do this, we use Parseval's theorem. So Parseval's theorem basically states that the total energy contained in the signal x of t sum across all time t is equal to the total energy of the Fourier transform spectrum x of f, sum across all of its frequency components. And mathematically, what that means is that the power in the time domain is basically equal to the power in the frequency domain. And in discretizing the continuous time form, we basically see here that all the integrals become summations, and they go from n equals 0 to n minus 1. All of these t's here become delta of t, and all the f's here become delta of f. Because this is modulus of x of f squared, we basically say that the discretized frequency part is known as x of m, and we still take the modulus of this being squared, because in the discretized version, x of m is a complex number. X of m is also referred to as the linear spectra. So, just recapping what I just now said, all the integrals have been transformed into summations, and the sample time interval delta of t is equal to 1 divided by this frequency, the sampling frequency, and the bin spacing, which is delta f, is equal to f of s divided by n, where n is the total number of samples. And the magnitude of x of m all squared is basically magnitude squared of x of m. And what we try to find out in particular is the use of the quantity magnitude x of m all squared to evaluate what is known as power spectral density of a signal. Visually, what this means is that the power spectral density of a signal only goes up from the 0 Hz or the DC component to the half of that of the sampling frequency, because we're going to observe this in a little bit, that you want to see why this is so. Now, in particular, if we recall the spectrum replication where we did any DFT or FFT, within that frequency range from 0 to half of sampling frequency, those values there only represented unique values, and this is only the range that we're going to be focusing on for the power spectral density. So let's actually look at an example to see how this is clear. So let's say we had that input sequence there, x of n, and we have the sampling frequency at 80 Hz. And then we evaluate the magnitude of the linear spectrum, which is basically if we find the FFT of x, we multiply it by delta of t, and then we find the absolute of x of m in order to get the modulus. The MATLAB code can be seen here on the slide in order to achieve this. So if we plot this, we basically see, remember that x of m here are going to be complex values, but we're concerned about the magnitude only. So we only obtain the magnitude values here for each one of the frequencies. And the frequency vector makes sense because half of the sample frequency was 40 vectors and delta of f was set to 10 Hz. If we observe the shaded parts here, we can basically see that they're repeated, and they're repeated about the center frequency, which is f of s divided by 2, and the DC frequency, which is at 0 Hz, is a unique independent variable accordingly. So we just can't really get rid of this because they're contributing towards the power of the signal, but since they repeat, we can just multiply them twice. It comes like we just add the same signal to each other because they're just a reflection around the center frequency here, which is f of s divided by 2. So in formalizing the linear spectra and satisfying Parseval's theorem, we basically get our g of xx formula here, which is 2 divided by t multiplied by x of m all squared, and this holds true for this range here, 1 less than m less than or equal to n divided by 2 minus 1. So this is for, I'm going back one slide here, this is only for this range here. We don't consider the DC component and we don't consider the FFS divided by 2 component. We just calculate the power here for this part. And that's why it's 2 divided by t multiplied by magnitude of x of m all squared. For the DC component where m equals 0, it's 1 on t multiplied by x of naught squared. And at the center frequency, which is f of s divided by 2, it's going to be 1 on t x of n divided by 2 all squared. So note that we only multiplied by 2 for the repeated sections, and the amplitudes at the DC component and f of s2 components remain unchanged, and they remain quite similar for an original definition of signal power. And visually what this looks like is like this, and we can see here that the DC component remains the same, the center frequency component, fs divided by 2, also remains the same, but these AC components here are now twice the magnitude of the original point that we saw from the previous graph. One thing to note is that the unit for power spectral density is volt squares per second or volt squares hertz. Basically, the power spectral density here, when we make sure that this relationship holds in the yellow block, such that 1 on n for the summation of all x of n squared can be the same as the summation of n on 2, where m equals 0 for gxx of delta f. Once the relationship remains the same, the Parseval's theorem holds true. In some cases, we may want to watch for unwindowed time series, and this may be in cases like if we're dealing with sinusoids. In such a case, we want to actually calculate the RMS power instead, because trying to find like the absolute power for this tends to be a little bit tricky. And RMS power for sinusoids in particular is a better way to represent the actual power of the signal, or the actual power estimate of a signal. For non-stationary signals, there are other methods to calculate or estimate the power spectral density, and they tend to rely on statistical modeling or stochastics in particular in order to do this. The techniques we saw, like the win-win techniques and so forth for the short-time Fourier transform, also apply here in particular. And MATLAB in particular has some examples in their help documentation as well as online resources as to how power spectral density is performed. So that brings us to the end of our spectral analysis lectures.